Then they have allosteric activation, which would be kind of the opposite. I focus on competitive enzyme inhibition and allosteric or non-competitive enzyme inhibition. I don't think it will save this, but we'll see what happens. Oh, you know what? It might, because it's in my thumb drive. It's not an Angel. See if I can move it over. Oops, can't move it over. Oops, can't do that either. Oh, whatever. That's A. Let's unsave that. I'll leave it alone. Okay. All right. Okay. And then feedback inhibition. You know about feedback inhibition. I don't know why feedback inhibition comes in here, but I'm going to ask about competitive and non-competitive or allosteric inhibition. You know about feedback inhibition, right? You did it in anatomy and physiology?
No.
No.
Allosteric control. Allosteric means the enzyme is controlled at something other than the active site. And I'm not going to focus on this, but just so we went through it once. Okay. If your enzyme has an accumulation of end product, so that the end product binds to the allosteric site, an accumulation of end product will change the enzyme so that it cannot fit any new substrate molecules. And I actually talk about this when I do, let me think. Can't remember. It'll come up again later. When we do induction and repression. Okay, so feedback inhibition is accumulation of end product shuts down the enzyme. I already have enough end product. Why would I break down more substrate to get more end product if I don't need any more end product? So the end product itself accumulates. When there's an excess of end product, it will shut down the activity of the enzyme. So you don't need to make any more. That's why you have allosteric sites on your enzyme. Because you want to control the activity of the enzyme. Remember, substrate concentration matters. If I've got an excess of substrate, I might want to keep running my enzymes and getting end product. But when I have an excess of end product, I don't need to break down any more substrate. So I'm going to stop the activity of my enzyme. It's reversible. It's temporary. Once you use up the end product, then the enzyme can go back to shape, can go back to binding with the proper substrate, and give you more end product. And that's feedback inhibition. Okay. Bacteria rely on their enzymes to catalyze the metabolic reaction just like we do, so that's how you can harm them with competitive enzyme inhibitors and non-competitive enzyme inhibitors. One blocks the active site, the other changes the shape of the active site. Okay, competitive enzyme inhibitors. These are your traditional bacteriostatic antibiotics. So what do I mean when I say bacteriostatic? Yeah, what's static? Stop. So bacteria, stop the bacteria. So bacteriostatic antibiotics don't go in and kill the bacteria. That would be bactericidal. Suicide, cidal. So bactericidal kills. Bacteriostatic stops. Stat is stop. Okay, so these are good magic bullets because I can usually find a compound that will fit the active site on a bacterial enzyme that's an enzyme that we don't have. Or our enzyme active sites are a little different, our substrates are a little different. So they're good magic bullets. Penicillin binds to the enzyme that makes peptidoglycan. We don't have an enzyme that makes peptidoglycan, so we don't care, right? Penicillin might be a good example of a competitive enzyme inhibitor because it's going to interfere with the enzyme that's needed to make peptidoglycan. So it's a good magic bullet because we don't have an enzyme like that. The problem is, if if I don't go in and kill all my bacteria right away, some of them are going to be alive, some of them are going to be exposed to the penicillin, and some of them are going to evolve resistance to the penicillin. So, that's the problem. Bacteria can develop resistance. Sulfa drug is one example. It's also covered in chapter 10 in your textbook. Penicillin's another example. The enzyme that's responsible for making peptidoglycan is called transpeptidase. You might see that word on your third test. Transpeptidase. We didn't really talk about the structure of peptidoglycan. Peptidoglycan's a net-like molecule, right? Everybody remembers that. What do you think holds that net together? Tetrapeptide bonds, little peptide bonds. So an enzyme has to make those linkages, those cross linkages in the net-like molecule. Penicillin interferes with that enzyme, so the peptidoglycan net comes apart. It can't go together. It's going to have holes in it. Remember we talked about this on the growth curve? When bacteria are in that log phase, that logarithmic growth, that exponential increase, they're all healthy, dividing rapidly, that's the time to get them. That's the time to get them with penicillin. That's the time to get them with bacitracin, because they can't make the transverse septum, that cross wall, that transverse plate. Okay, penicillin and bacitracin and many other antibiotics are in a category called beta-lactam antibiotics. In chapter 10, they'll show you the structure of the beta-lactam ring. I don't expect you to memorize the organic formula for, the molecular formula for penicillin or bacitracin. Just know that this beta-lactam ring is the important part of the molecule. That's what makes the antibiotic active. That's the part that binds to the active site on the enzyme. Some bacteria have evolved an enzyme called beta-lactamase, which destroys the beta-lactam part of penicillin and bacitracin. So those bacteria are called beta-lactamase positive. If you're beta-lactamase positive, what does that mean? You have an enzyme to break down the beta-lactam antibiotic. You're resistant to penicillin and bacitracin and beta-lactam antibiotics because you've evolved an enzyme that breaks it down. It can't hurt you. What if your patient's chart says your patient has a beta-lactamase positive gonococcus? What does that mean? What? You have penicillin-resistant gonorrhea. Most gonorrhea is penicillin-resistant nowadays. So when you see beta-lactamase positive, that means it's resistant to penicillin, resistant to bacitracin, resistant to those category of drugs that break the transpeptidase enzyme or interfere with the transpeptidase enzyme for making peptidoglycan. This is my favorite part of the whole class. You know how I like the history part, right? In the olden days, they used heavy metals and halogens. Remember your periodic table? Mm-hmm. Your periodic table has a whole row of halogens. Mm-hmm. Anybody took chemistry? Holden took chemistry, yeah. Right? There's a whole row of chlorine, bromine, fluorine, iodine. Those are all halogens. Can break down enzymes, active sites, can destroy the enzyme, not really by denaturing, but by altering its shape. Chlorhexidine gluconate. Chlorine in there, right? Is anybody familiar with chlorhexidine gluconate? No. Final exam question. Telling you now. What's chlorhexidine gluconate in?
It's what we're put on iodine solution. It's what we use for pet surgery.
Surgical scrub and surgical prep. Guess who launched it in the United States? me and a bunch of other sales reps. This was our product, Hibiclens was our product. So whenever you see a bottle, like my Lanta and Hibiclens, that's that turquoise blue, that was our company color. So years ago when I was a pharmaceutical sales rep, we sold my Lanta, and we sold Hibiclens surgical scrub, we sold Tenormin for blood pressure, and also the first breast cancer drug, tamoxifen. So we launched some pretty serious drugs. Chlorhexidine gluconate is the compound, the antibacterial compound, the antimicrobial compound in a surgical scrub called Hibiclens. How does it work? It works like a poison. It's a non-competitive enzyme inhibitor. It harms the shape of the enzyme of bacteria. Okay, I have a little thing here. Somehow I got to figure out a way to get this into a PowerPoint slide, but they're little pictures I cut out from a magazine. I don't know if you can see them, but I love these little pictures. Well, first of all, Halloween's like my favorite holiday. But see this funky little container? And it has absinthe in it. In the olden days, the way they got their kicks was to get this, it was a form of alcohol, but it was, did I write it down? Absinthe. It was like a concentrated form of alcohol, and maybe mixed with other chemicals, and they would dispense it onto sugar or sugar cubes, and then eat that, and they'd catch a buzz. But not like alcohol on steroids, like much bigger buzz than alcohol alone. And then they also have these little jars for Halloween. Belladonna. Did you ever take belladonna? There's a good buzz. Belladonna will relax your digestive tract, so if you have spasms in your digestive tract. But if you take belladonna from the plant,